Hi everyone. Today we're going to be looking at our notes for Intro to Inverse Trig Functions. So I want to start off by just talking about what is an inverse function. Well, we know that something like an inverse operation is an operation that undoes another operation. So for example, we're looking at, say, like addition and subtraction, multiplication and division, also things like squaring and square rooting. We'll see logs and exponentials are inverses of one another. So an inverse function, so if we're talking about a relationship between two quantities, x and y, the inverse function switches that x and y. So it switches the input of the original function, or x, with the output, or y. Okay? So let's take a look at what this looks like for y equals the sine of x. Okay, so we have our function, y equals the sine of x. If I wanted to switch x and y, then I would have the equation x is equal to the sine of y. And if I wanted to solve for y, I would have to undo this operator here, taking the sign of whatever y is, right? So undoing this operator, this sign, we do the inverse sign of both sides. So we're going to write this as the inverse sign of both sides. So we have the inverse sign of x is equal to the inverse sign of the sign of y. So notice that we're taking the inverse sign of both sides. And we're going to denote it using this -1, this symbol up here. It's kind of like a superscript up here. Looks like we're raising to the power, but be very careful. This notation here is not raising to the negative first power. This represents the inverse of the sign. Okay? On the right-hand side of this equation, we have the inverse sign of the sign. So because we are using inverse operations here, the sign and the inverse sign, they undo one another. They cancel each other out, and all that's left is the argument of the sign here, y. On the left-hand side, we're just left with the inverse sign of x. Okay? So the notation here for the inverse of these trig functions, remember like in algebra and geometry, we talk about inverses of functions. We use that f inverse of x, or f to the -1. It looks like f to the -1. It is not f to the -1, but it looks like that. It's a similar notation for those trig functions. So we would say the inverse of sine is sine inverse, inverse sine of x. We have inverse sine, inverse cosine. So that would be like cosine and then that -1 of x. So inverse cosine of x. We have inverse tangent of x. And then we can also do that with the reciprocal functions, secant, cosecant, and cotangent. So we have the inverse cosecant of x. Okay? So one thing to note here, is this statement true or false? The inverse sine of x is equal to 1 over the sine of x. You can pause the video, think about it for yourself, and then unpause when you're ready. The answer to this is false. Okay, we already know what the 1 over the sine is. 1 over the sine of x is equal to our reciprocal function, the cosecant of x. Okay, the cosecant of x is not equal to the inverse sine of x. Okay, these reciprocal functions are different than the inverse function, so be careful. All right, so when we think about trig functions, remember the input of a trig function is always going to be an angle. When we evaluate, say, like sine of 30 degrees, the input of the sine there is the 30 degrees. It's an angle. Well, remember for inverses, we switch the input and output. So therefore, the output of an inverse trig function is always going to be an angle, okay? Which means that the input is always going to be a value, and then the output is an angle. So just like how our regular trig functions, the input is an angle and the output is a value, the input to a inverse trig function is the value, and then the output is the angle. Okay? I also want to note the difference between these two examples right here. So here on the left-hand side, we have sine of x is equal to 1/2 versus the inverse sine of 1/2. Okay? So the sine on the left-hand side, sine of x is equal to 1/2. This is an example of an equation. We have two sides to it, and it's separated by an equal sign. If I wanted to solve this equation, we would take the inverse sine of both sides, and we would get solutions for x. We would get all values x that make this equation true. So equations we solve. On the right-hand side, we have the inverse sine of 1/2. There is no equal sign here. This is an expression. Okay? We can evaluate expressions, or in other words, we find the single numerical value that this is equivalent to. Okay? So again, this left-hand side in this equation that we solve, we find all values for x that makes that equation true. It could be many solutions. It could be infinitely many solutions. On the right-hand side, we have the inverse sine of 1/2, which evaluates to a single value. This is an expression. We evaluate it. Okay? So let's consider y equals the sine of x. Again, this is our parent function, just that trig function y equals the sine of x. If I wanted to graph this function, well, I know that the parent function is going to start at the origin, and it's going to go up and hit a max, go down, hit a min, and then return to the midline. This would be one cycle. And I can go ahead and extend that behavior. This function's periodic. And it also continues in this same behavior on the left-hand side in the negative x values. Okay, so this would be our function here. This is just a rough sketch. Okay. If I wanted this function to have an inverse, then it must be 1-to-1. It must pass the horizontal line test. Well, by looking at this graph does not pass the horizontal line test. For any horizontal line that goes through the function, it goes through infinitely many times. There is no way that we can draw a horizontal line and pass through the function exactly once. Okay, so this fails the horizontal line test unless we restrict the domain. So let's take a look at this function here, and let's see if we can find a domain, or a restriction on the domain rather, that's going to allow this function to pass the horizontal line test, which would cause its inverse to be a function. Okay, so looking at this, I noticed that if we were to restrict the domain, I'm going to use a different color here. If we were to restrict the domain from right about here to here, which as a reminder is for the parent function, negative pi halves to pi halves. Notice what happens in this function. We get this piece here, and it comes up. It goes from the minimum to the maximum. Okay, so we get this piece here. If we were just looking at this little blue piece, this is going to pass the horizontal line test. There, for all values here, I can draw a horizontal line, and it's going to cross through the function exactly once in any of those places, right? So if we restrict the domain to negative pi halves to pi halves, then it passes the horizontal line test. The inverse is then a function. Okay? The range of this piece, so y values, we're going from -1 to +1. So by restricting the domain, we also can find the range of -1 to 1, which is the same actually as the original function without any restrictions. Okay? One thing I want to note is that for the domain from negative pi halves to pi halves, notice that this on the unit circle is going to be quadrants 1 and 4 on the unit circle. Okay? Okay, so let's go ahead and evaluate here. So we have the inverse sine of √2/2. So we're saying for what angle, remember the output is an angle, for what angle is the sine equal to √2/2? Between this interval over the domain, negative pi halves to pi halves. So remember our √2/2, that's going to be our reference angle of 45 degrees or pi fourths. And we're looking over the interval negative pi halves to pi halves. So our answer is going to be in quadrant 1, that reference angle of pi fourths. Our answer is pi fourths. Okay? As a reminder, our sine, our y value, is going to be √2/2. So we're looking for, where is that y value, √2/2? What's that angle right there? Okay? So that's going to be our pi fourths in quadrant 1. For the next one, we have the inverse sine of negative √2/2. Again, that's our reference angle of pi fourths, but now it's negative. So if I were looking at the coordinate plane, we're looking at negative y values, so a negative √2/2. Now, of course, this would give us quadrants 3 and 4, but because we've restricted the domain to quadrants 1 and 4, we need to just consider this one triangle here with a negative √2/2 as our vertical component. That reference angle there is going to be pi fourths, but in quadrant 4, over this domain, is going to be negative pi fourths. Okay? So these evaluate to pi fourths and negative pi fourths, respectively. Double check that your answers are within the domain here. So these are the domain and range of the inverse side. Okay? So go ahead and flip the page. Number 10, which angle specifically within the range, negative pi halves to pi halves, again, quadrants 4 and 1, have the given sine values. So looking at this, we have the inverse sine of root 3 over 2. We're looking at the positive value, root 3 over 2. So that must be a positive y value in quadrant 1. So if I draw my triangle here, we have root 3 over 2. My horizontal component is going to be 1/2. My reference angle, that angle across from the root 3 over 2, is going to be 60 or pi thirds. So my answer, the inverse sine of root 3 over 2, is going to be pi thirds. Okay? Our reference angle is going to be our inverse sines here. Okay? Over here we have negative root 3 over 2. So again, we're looking in quadrants 3 and 4, but only in quadrant 4 because of that restricted domain of negative pi halves to pi halves. We're looking at quadrant 4. Again, that vertical component is negative root 3 over 2. So then our reference angle is going to be pi thirds. In quadrant 4 is negative pi thirds. Okay? For inverse sine of 0. So remember, sine corresponds with y. For what point on the unit circle is y 0? The answer is 0 radians and pi radians, but we're only looking between negative pi halves and pi halves, so then our answer is 0 radians. And finally, the inverse sine of negative 1. So we're looking at where over the domain from negative pi halves to pi halves is the sine equal to negative 1? Well, there's only one answer here, negative pi halves. Okay, that's the negative y-axis there. Okay, now let's consider the cosine. So let's go ahead and draw that graph again. So the cosine, remember, starts at a maximum, goes down, hits a minimum, and then ends that first cycle with a maximum. Okay, so here's one cycle. We'll go ahead and continue the graph. This is periodic, so it continues on in both directions and repeats the same behavior. I'm going to use a different color. So how can we restrict the domain of the cosine so that the inverse is a function? Well, we can't restrict it from negative pi halves to pi halves again because we're not going to be able to pass that horizontal line test. However, what if we start at 0 and then end at pi, right? So if we start at 0 and then end at pi, notice this piece right here. We're starting at a max and we're going down to the minimum. This section here is half of the function, half of the one cycle of the parent function. So this from 0 to pi does pass the horizontal line test. This does have an inverse function. Okay, so if we restrict the domain, again, from 0 to pi, the range is going to be from negative 1 to 1. Again, we hit all those values. I'll switch back to red. From 0 to pi, on the unit circle, this is going to be quadrants 1 and 2 on the unit circle. Okay? So let's consider now number 12, the inverse cosine of root 3 over 2. Okay? So we're looking at the positive x value, root 3 over 2. We're looking in quadrants 1 and 4. While restricted to only 1 and 2, we have that x value is root 3 over 2. Vertical component is positive 1/2, quadrant 1. So then our reference angle must be 30 or pi 6. Okay? So the angle for which this is true, or what this evaluates to, is pi 6. Where we have a negative value as the input of the inverse, we're looking at negative root 3 over 2. Well, that's quadrants 2 and 3 with a restricted domain in just quadrant 2. We have a negative root 3 over 2 as our horizontal component, and then we have a positive 1/2 as our vertical component. The reference angle is pi 6 in quadrant 2 is 5 pi 6. And finally, the inverse cosine of negative 1. There's only one value, that one angle for which the cosine is equal to negative 1. Over this domain, the answer is pi. Okay? So remember, restricting the domain, there's a few ways that we can remember which quadrants we're looking at. So one way that we can do this is representing this like verbally. So we can write out. We know that sine is the inverse sine, the domain is going to be in quadrants 1 and 4. So we can write it vertically spanning quadrants 1 and 4, whereas cosine is in quadrants 1 and 2. Okay, so one way to remember this is both of them share an s, so we can write them out in this orientation. The same is true for the reciprocal functions, secant and cosecant. So again, the reciprocal of cosine is secant, the reciprocal of sine is cosecant, so therefore the inverse secant and the inverse cosecant are going to have the same domains as the inverse sine and inverse cosine. And then finally, for tangent, the domain of the inverse tangent is quadrants 1 and 4 from negative pi halves to pi halves. And then finally, the domain of the inverse cotangent is from 0 to pi, quadrants 1 and 2. Okay? All right, so a few more examples. Let's go ahead and consider the inverse tangent of root 3. This is the same as saying the inverse tangent of, well, what's going to cause the quantity to be equal to root 3? If we have our root 3 over 2 divided by a half, that's the same as multiplying by 2, so that would cancel out that denominator. So remember, the tangent is the ratio of y and x, so this is where our vertical component, our y value, is root 3 over 2, and our horizontal component is 1/2. Okay? So this exists for a reference angle of pi thirds, and we're looking at where the inverse tangent is positive. So we're looking at quadrant 1. Okay, so a reference angle of pi thirds in quadrant 1 is simply pi thirds. The same thing here, but now our root 3 is negative. This would now then be in quadrant 4 or 2, but again, over that restricted domain, we're looking at inverse tangent from negative pi halves to pi halves. This is going to be in quadrant 4, or an answer of negative pi thirds. Okay. Cotangent, where cotangent's equal to 1. All right, so remember which ratio of side lengths would cause this quantity to be 1. The only answer for that is our reference angle of 45, or pi fourths. So that's our root 2 over 2 over root 2 over 2. Okay, so again, root 2 over 2 over root 2 over 2 is equal to 1. So we're looking at a reference angle of 45 degrees, or pi fourths. This is a positive quantity, and again, we're looking at a positive quantity in quadrants 1 or 2. So both positive here, x and y. We would have quadrant 1, so we're looking at pi fourths. Finally, if we're looking at inverse cotangent of negative 1, this would be where one of these quantities, x over y, is negative and the other is positive. Okay, so this must be in quadrant 2, and again with the reference angle of pi fourths over the domain 0 to pi, our answer is 3 pi fourths. Okay. Finally, the inverse cosecant of root 2. So seeing that root 2, that cues me that this is a 45, 45, 90 triangle, or the reference angle of pi fourths. So this is a positive root 2, so we must be looking in quadrant 1 with the reference angle of pi fourths. And finally, the inverse cosecant of negative root 2, again from negative pi halves to pi halves. This is going to be a reference angle of 45, or pi fourths, in quadrant 4 because we're looking at a negative quantity. So we're looking at negative pi fourths. Okay. All right, so these have been our notes on inverse trig functions. Remember, the input of the inverse trig functions is a value and the output is an angle. And then finally, we restrict the domain so that these inverses are functions. Okay, we're going to get a lot of practice on this, so we'll see you tomorrow. Have a great day, everybody. Goodbye.